our infra developer experience team, and yeah, I'm going to talk about like debugging for Erlang. Okay, cool. So debugging, how does debugging typically look in Erlang? I would say there are like three options. One is using tracing directly or using some library like Redback or whatever. Tracing is super cool. I like to say that it's like Erlang superpower. You take like a running node without changing any code. You suddenly get logs of stuff going around. It's super cool. It has its cons, so it works great if you're like troubleshooting something on a live cluster or live system, but not everything is a live cluster. Maybe it's like a short running program, like a test or a CLI app. And also, I mean, we shouldn't get to the point where you need to troubleshoot stuff in production, but it can happen. So if you're not using tracing, well, the other alternative thing is just put print statements everywhere. That always works. You get like long feedback loops, like you need to change the code, and wait for everything to rebuild, run your test again or whatever, and see what happened. And it's a bit messy. You need to clean up things at the end before sending your pull request or whatever. And then OTP, since time immemorial, comes with a debugger application. It's like sort of traditional step debugging. This is good. Like a lot of people like this kind of debuggers. They are used to using them, especially like newcomers to the language that would like to use it. In practice, what we find is that when people were actually trying to use the debugger, they got stuck for various reasons and just give up and not use it. As I said, I work in a developer experience team, and there is a thing that Meta does that is nice, that it runs regular satisfaction surveys across all engineers to see like what tools are working well. And systematically for many years, we're getting very bad signal regarding debugging. One typical comment that they will say is like the Erlang debugger always times out. What this means, if you try to decode, is people would, let's say, put a breakpoint on a handle call from a Gen server and then run their test or whatever. The process executing the handle call pauses in that breakpoint. The user starts inspecting variables and whatnot. But the caller of the Gen server had a timeout of whatever, 5 seconds. So by the time the user ends and decides what to do next, the rest of the system already timed out and crashed. And in a way, like their debugging session was ruined. So our first impression was that if we wanted to solve this thing, we need an Erlang debugger, a step debugger, to stop the world, like not just the process that keeps the breakpoint, but every other process on the VM. So we could say, okay, let's take the debugger the debugger application that comes with OTP, and extend it so that it does this stop the world thing. Now, we didn't think that was a good idea, a bit because of the way this debugger works. So if you're not familiar with it, the way the debugger that comes with OTP works, what it does is if you set a breakpoint on line 42 in function foo, what it's going to say, it's going to ask the VM to hijack the execution if function foo is ever run. So instead of running the actual code, the execution goes to this Erlang interpreter that will load the syntax tree of the module and start interpreting it. Because it's interpreting it, it can know the value of all variables involved, decide if it needs to stop on a breakpoint step or whatever. But like, let's say we hit a breakpoint, and let's say that we manage to pause every process on the virtual machine. The interpreter has no idea what's going on with the rest of the processes. Like, we cannot say like what was the state of the caller, like what were the process that called the current gen server or whatever. Like we would be blind. So we decided to embark in an adventure to try to replace the debugger that comes with OTP with a new one decided to provide like good visibility about everything that's going on. The main changes, I mean, the main components of this were changes to OTP itself. We needed to extend the VM with new debugging primitives. We needed to extend the compiler to have like some kind of debug mode where it emits more debugging information on the VM files. With those, we wrote like a new debugger, like an Erlang application that gives us like all the common primitives on a step debugger. And on top of that, what it's called like an adapter layer. It's like some kind of front end for the debugger that can talk a protocol that most IDEs can understand. So we can use it with VS Code, Emacs, Beam, IntelliJ, whatever. So the rough architecture is something like this. The user is using their IDE, whatever VS Code. They launch a new debugging session. This creates a new node, which we call the debugger node. This thing is talking through this adapter protocol with VS Code to decide like we set a breakpoint to get some variables, whatnot. And it also connects via right now Erlang distribution to the node that it's actually going to be debugged. This could have been a running node, a node that was already running in the system, or it could be a node that is launched as part of the debugging session. And connecting, what it means is the debugger node using distribution will inject support modules on the debugging node, and it will start a special gen server, what we call here the debugger process, that will use this API provided now by OTP to control what happens in the execution of the node. And then the debugger node controls the debugging via this debugger process. So yeah, let's see how things more or less works. What were the changes that we needed to make? Let's begin with breakpoints. If we want to have breakpoints, the first thing that we needed to do was extend the compiler. So the Erlang compiler now has a new compilation option, a flag called beam debug info that if you program with GCC, it's similar to using -g in GCC, like saying like I want to have like a debug build. This does a couple of things that I'll discuss next. The first one is that a new bytecode was introduced, debug line, and the compiler will emit this line on the bytecode at the beginning of each executable line. This is similar to other instructions that the Beam already had. There is one called executable line that is used for connecting coverage. There is one called line that is emitted at fewer locations. That was for being able to reconstruct in the stack trace what are the colors at each point. This one is similar. It is emitted at the beginning of every line, but it needs to provide more information. In particular, it needs to provide how many registers are live at that point, because the VM is going to need to save them, stash them in a new stack frame, make it safe. And the compiler also ensures that at this point, it's always safe to deschedule the process, which means ensuring there are no gaps. So all pointers are safe, are well defined, so it's okay to swap out the process. Next, we needed to extend the VM with support for this. There's a new flag for the Beam called class D for debugging. So if you have your source file was compiled with the new Beam debug info, and you are running it in a Beam that was started with the +D option. Then when let's say the just-in-time compiler is loading a module and it finds one of these instructions like debug line in line 42 or whatever, it generates something that looks like this tiny snippet of code. The important things are it emits an unconditional jump to this block here, and in between it adds a few instructions. So under normal conditions, there is an overhead of one jump, and these things are ignored completely. And it also takes a note in some internal table the Beam always had of where in the code line 42 starts. So with that, we can then add a built-in function to toggle a breakpoint. What does toggling a breakpoint mean? If the caller says, I want a breakpoint on line 42, it first needs to check this line table to find where in code, what's the offset in code, where the line 42 starts. It knows that there should be a jump here, and then it mutates the code. It replaces the unconditional jump by another unconditional jump, but this time it sends it to this small block. What this small block does is, puts in a register the number of Beam registers that we need to save on a stack frame, and then run some common logic that will create dynamically a stack frame, save all the records, put the process in a waiting state, and send a message to this debugger process that was registered as the debugger for the node. This, by the way, is except for the part where we need to create a stack frame on the fly, is the same infrastructure that drives, let's say, tracing. For tracing, something very similar happens, but at the beginning of the call, beginning of the function, here we need to be able to handle it at each line. But most of the infrastructure luckily was already there on the Beam. So yeah, with these two things, we get, yeah.
So is this debugger primarily implemented in the source to bytecode compiler, or is it kind of that plus the engine is aware of the?
It's a combination. So there's, for breakpointing, we are using this support from the module loader. We had to add another built-in functions to be able to inspect registers that I will discuss in a couple of slides. And these are like very low-level debugging primitives. And then we build the full debugger as an Erlang application on top of those primitives.
Okay, so you like have more exposed functionality in the host that's being used by the debugger.
Yes, okay. Yes. So with this, we have enough to be able to set a breakpoint and get a process on a waiting state and a message sent to a debugger. Then there's the part about like stopping the world. Here we see like what you would see on, I don't know, VS Code. When a process hits a breakpoint, this is a view to show like shows every process, and you can do the stack and whatnot. But you see that it says that they are all post and one is post on a breakpoint. So conceptually, even though like stop the world is in the title of the paper, it's like the easiest part, because for a long time, Erlang had like a suspend process if that would mark the process as not to be scheduled until you resume it. So conceptually, when something hits a breakpoint, the debugger can just call this function on every process running. There's some details, but it's mostly it. The thing is, that would not have been enough for what we wanted to do because this problem. So suspending the process was only marked as do not schedule. But we have the problem with receive statements and timers, the one that motivated this problem. So internally, this is an implementation detail of the Beam, but when a process starts executing a receive statement, the first thing that happens is that if it has an after clause, a timer is set for 5 seconds, and it will check if there is something in the mailbox, and if there's nothing in the mailbox, the process will be descheduled and be in a waiting state. And what can happen is that a message arrives and it's processed, and if it's processed, the timer is cancelled, or 5 seconds pass, the timer go off and sets a flag in the process saying like timeout. And the process will be scheduled once again, and because the timeout flag is there, execution will continue here. So suspending the process is not enough if we don't do also something with the timers. And so we had to extend the suspend process beef to deal with it. Conceptually, this means when suspending a process, we need to check if it has a process timer, stop it, but take a note of how many milliseconds remaining so that when we resume, we create a new timer for that amount. And yes, with this, we can give this illusion that the node is stopped. As I said, ideally, we would just suspend every process except the debugger process. In practice, this doesn't work because we are using distribution to connect the node being debugged with the debugger. So if we kill every process, if we suspend every process, the distribution connection goes down and then the node will be break effectively. So we use a heuristic. We suspend all user processes. The current heuristic is if a process is in the current application, we exclude it. And there's a couple more system processes that need to be excluded. And everything else we suspend. This, for now, it's been working well as a heuristic, but it's user configurable. So for settings where this doesn't work, it can be changed. And then the question is how we suspend them. Right now, we did the simplest possible thing that could be done. That is, list the processes, go one after the other, and suspending, no concurrency, nothing. In fact, when we try to be a bit smarter and use like an asynchronous option that exists, where you can like suspend the process, but not wait until it's effectively suspended, the results were even worse. So for now, the latency is acceptable. I think it's working well, but there's room for improvement. So yeah, inspecting variables. So what we want to be able is to show what are the value of the variables in the running process. I won't go into a lot of details, but just need to know that in the Beam, in the virtual machine, there are two kinds of registers, what are called X registers, which would be like what one would call a register, any kind of register machine, things that ultimately tend to end up in an actual processor register. And Y registers are just a name they give to slots in the stack frame. So we are given stack frame, they are numbered 0, 1, 2, 3, they're called Y registers. So this new Beam debug info option that was added to the compiler makes it so that it creates a new section on the Beam with debugging information in the way of a table that says the beginning of line 42, variable foo is stored in X3, and variable var is stored in Y13. And we, on top of that, we added built-in functions to be able to pick the value of any X register or Y register in a suspended process and do the same for all the contents of the stack. And that's mostly it. So with this, we can set breakpoints. Something stops, we pause the whole VM. We can show the values of the variables, show the stack. Now, the user wants to step into, like, what do we do? I think we would have two alternatives that I can think of. One is to make the VM aware of stepping, like add some kind of flag to the process where a process can be in a stepping state, and in the next call or whatever, it tells you something. I thought at least that would add a lot of complication and probably performance issues in the VM. So the next thinking is like a C debugger or something like GDB, like it only has a breakpoint instruction that the CPU gives it, and with that, it simulates everything else. So let's do the same. So stepping is simulated at the level of the debugger. I mean, probably this was long known for 50 years, but I never thought before how you actually implement stepping based only on breakpoint. So it was fun to think about it, but I mean, it's not nothing very new. The idea is, well, first, you need to have some bookkeeping to know that some breakpoints were set because the user wanted, and some breakpoints are set because certain process is currently stepping. So that's some kind of conditional breakpoint. We currently don't have any kind of debugging information that tells us at each line what is the next possible lines where the control could flow. We just over approximate and set these funny breakpoints on all the lines of a function. That's been good enough for now. Then we also need to consider the callers, all the functions that are in the call stack, because maybe when you step, you end the execution of the current function and you want to land in the caller. So you need to set a breakpoint in the function of the caller as well, just considering this. And when you're stepping, also the function could raise an exception. So you need to identify along the stack where the exception handlers are that we can, with this if we added, and set breakpoints on those functions as well. And then it gets a bit tricky when you do things like you want to step over on a recursive call, and you don't want to enter the recursive call. So how are you going to tell apart these two cases? How do you know if you are stopping on the right frame? So you also need to keep track of what you expect the stack to look like when the breakpoint hits for you to stop, so that you make sure that you stop at the right point. So that's mostly the idea. Then for stepping, so this covers stepping over, so ignoring the current call and just go to the next line, and stepping out. For stepping into a call, you sort of need to know what's the call target, so that you can set a breakpoint in that function. We did two approaches. Initially, we were using the abstract syntax tree to figure it out, but it is a bit of a mess, and we are essentially redoing the work the compiler does. So we extended the compiler so that it adds this information at each line, which are the possible call sites as debugging information. And we can, in principle, support dynamic calls as well, because we can know that a dynamic call involves variables, and we know the values of the variables. Okay, so something I didn't mention so far. There is a cost to this. The cost comes from two places. One, the overhead of these mini trampolines, which I expect was going to be negligible because it was being used for tracing anyway. And the other is when you compile something with this beam debug info, in order to be able to keep track of the value of the variables, it needs to disable some optimizations. I'll discuss one in a moment, but like one set of optimizations that are disabled right now are, I think, all the ones that have to do with binary handling of binaries, pattern matching, etc. This is because optimizations were not keeping track of where the variables end up, or they might end in multiple places or whatnot. So we just turn it off. And the question is good enough? Like, will everything crawl to a halt? So, of course, if you do a benchmark on code that, let's say, does a lot of binary processing, the numbers are going to be terrible, but this is expected because like that's why the optimizations were introduced in the first place. So, but if you look at more realistic code, what we did as an experiment is take a very large number of real tests used at WhatsApp, and there were like 2.5 days worth of execution, one after the other, and run them with and without debugging compilation and see how long it takes to run these 2.5 days of tests. And the difference in practice was quite good, right? What this means is that all the overheads are in practice in message passing, input output, etc. It's not really an issue, and we've been using this debugger since the beginning of the year, and people are happy. So I assume that it's not really a big of a problem. Okay, so this was a longish project, and you really want to get to something that works quickly, and you need to take some shortcuts along the way. So let's discuss the shortcuts that the main ones that we took, and what we do. So I said, for instance, that we have like debug information that says at the beginning of each of this line, these are the variables that are available. And we use the line, we could have used line and column because that is the granularity the compiler gives us. Like the compiler annotates its expressions with line or line and column. But it's not true that every line, the code for every line ends up in a single place in the bytecode. Like the easiest example is function inlining. Like if you look at line 42 of a function that gets inlined multiple times, well, line 42 will end up in multiple places, and the context in each place is going to be different. Where the variables are going to be located, it's going to be different. So how do we support this? Well, right now we can't. So no function inlining when compiling in debug mode. There is a similar example with comprehensions, like generators and matches get compiled in different places. So you either say that the beginning of the line is when the generator is executed or on each match. Right now, I think we do it on when the generator is executed, which means that when you are stepping over code with comprehensions, it looks a bit weird because the execution never goes back to the match. How to solve this? Well, we need the compiler to have some finer notion of for each expression, we need some kind of, I don't know, like an expression ID, and then maybe multiple expression IDs mapped to the same location, but then the VM needs to be able to deal with those expression IDs as well. So it's doable. It will require a bit more work. And slightly related to this, for me, it's like the other, like almost the same problem. When if a process is paused, we want to see the value along the call stack, like what were the variables of the caller of this function. We can show the value of the registers, but we don't have a way to map it to a variable because the information that the compiler gives us tell us what were the variables stored at the very beginning of the code for that line. but by the time the actual call happened, things can have changed already, and that information is not accurate anymore. So we cannot show it. We need some way to give this information almost by expression, not just by line. And if we can provide this information per expression, would be nice if we can have like the ability to set breakpoints per expression, not only per line, because then stepping can be done in a more granular way. Conditional breakpoints, we use them only for stepping right now. They're a bit slow, essentially because the evaluation needs to go through the debugger process, and that becomes a bottleneck if you are doing this on a hot path. Ideally, we should be able to evaluate this on the VM itself. And there were some other issues. I won't go into details. The most annoying one now it's fixed, which is that we were not, like, the compiler is very aggressive, naturally optimizing variables that are not referenced anymore. But then it would mean that when you hit a breakpoint, the user wants to see what were the arguments to the function, what is the variable mentioned in the line above, and they were not visible. Now, for next version of OTP, there's going to be a flag to relax this condition. Like, it's a trade-off in memory usage, but we've been trying it out and it looks to work pretty well. And yeah, I think that's mostly it. So the OTP extensions, most of them made it already to 28.1. Some are still in a pull request state, but we hope they're going to be merged soon. And anyway, the EDB debugger can work on, like, with only those extensions merged. So this is good. This is available on GitHub. People can use it. The easiest way to use it is if you are a VS Code user. There's like the Erlang language platform is an extension for VS Code that my colleagues at WhatsApp build and maintain. This comes with equalizer and whatnot. It's a super nice extension, and now it comes with the EDB debugger as well, and some convenient to be able to launch tests and have them run under the debugger. So yeah, I think that's funny. Thanks for attention.
Let's see, we have 1 minute left in case there are some questions.
Yeah. What kind of feedback did you get from your users? I imagine it must be interesting because they're used to using things like tracing.
Yeah, so they were not using tracing locally. I think it was print statements or yeah. I think so far it's been happy. I get perception in the last